Hey everyone. Well, you can see video number 9 here is longer than normal. That's because I've got some extra special content for you involving the very important idea of independent events. This is my first video introducing this idea. I will be solving for a probability by using an assumption that two events are independent. And that's a common thing to do in probability, is to assume, even if you don't know for sure, that two events are independent or unrelated to each other. I also want to generalize the problem. I'm doing a modified version of question number 11, and the extra part down here is my modification. So let's read the problem. An actuary studying the insurance preferences of automobile owners makes the following conclusions. Number 1, an automobile owner is twice as likely to purchase collision coverage as disability coverage. So collision coverage covers the automobile, disability coverage covers the person when they get hurt. Okay, but they're twice as likely to cover the collision coverage. 2, the event that an automobile owner purchases collision coverage is independent, there's the key word, independent of the event that he or she purchases disability coverage. Unrelated. If you know they've purchased collision coverage, it doesn't affect your assessment of the chances that they've purchased disability coverage and vice versa. The conditional probability of purchasing C, given that they purchased D, for example, is equal to the ordinary probability of purchasing C, and vice versa. You can switch the C and the D around. That's what independence means. Part 3, the probability that an automobile owner purchases both collision and disability coverage is 0.15. Calculate the probability that the owner purchases neither collision nor disability coverage, meaning not collision and not disability coverage. And again, here's my extra part. Calculate the same probability of purchasing neither collision nor disability in the case that the probability from part 3, this 0.15, is arbitrary. It's an arbitrary number I'm calling lambda, like I did a couple videos ago to just talk about generalizing problems. Also asking a similar question as back then, for what values of lambda can this problem be solved? Lambda itself being a probability must be between 0 and 1, but as a couple videos ago, lambda could affect the answer as well, and that answer being a probability has to be between 0 and 1, so that could put further restrictions on the value of lambda. Now you can see I've pre-made a Venn diagram here with rectangles rather than circles, and I purposely made the rectangles to have the right areas. The black rectangle represents the sample space and has an area of 1. And the red rectangle represents the event C, and its area ends up being its probability, which we haven't calculated yet. These numbers you could ignore for the moment as far as, how did I get them? I'm going to calculate them as part of what I do here. The area of that is about 55% of the total area. So that's C, purchasing collision coverage. The blue rectangle right here is D, purchasing disability coverage, and its probability ends up being about 0.27, so its area is about 27% of the whole area. The rectangle between the blue line there and the red line there is the intersection. They purchased both C and D. And the rectangle over here is that they purchased neither. This is C prime and D prime. Okay? And it's the probability of that we're after. Does end up being about 0.33. That is the answer, and that's choice B in the sample exam problems. So the answer ends up being B. But let's go through the steps of solving the problem now. So we'll solve the problem, do the algebra. I want to show you what independence means, not just based on the assumption here, but also intuitively in terms of decks of cards. I'm going to show you a picture of a deck of cards to help you think about it, and then at the end we'll do some cool things on Mathematica. All right, take it step by step. So 1 says the automobile owner is twice as likely to purchase collision coverage as disability coverage. The probability of C is 2 times the probability of D. That's our first piece of information. Second piece of information is that those events are independent. Like I said a few minutes ago, that means the conditional probabilities are equal to the ordinary probabilities. Oh, you got to be careful to get the order right. The conditional probability of C given D is the same as the ordinary unconditional probability of C. And vice versa, if you switch the roles of C and D around, the conditional probability of D given C is the unconditional probability of D. That's independence. Now I'm assuming these events are independent to solve the problem. And that is actually a common thing to do, even if you don't know it's definitely true. And in fact, you might say it's very rarely going to be exactly right that these are going to be exactly equal. But if it seems reasonable to assume, that's a common thing that people do in real life when they try to apply probability to real life. Before we use this information, I want to illustrate the idea of independence with a deck of cards. So here you see I've got a picture of a deck of cards. Standard deck, 52 cards. You've got 26 black cards, 26 red cards. These things have names. This shape that you see here, that's called a club. This is a spade, this is a heart, this is a diamond. So the clubs and spades are blacks, the diamonds and hearts and diamonds are red. You've got the face cards over here, the jack, queen, and king. You've got the aces over here, and then you've got the numbered cards in here. There are certain events, if you shuffle a deck of 52 cards and randomly pick out one card, there are certain events you can certainly think about, no pun intended. You could think about what is the probability that the card is red, for example. And you could also ask, what is the conditional probability that the card is a heart if you know it is red? As an example of a probability you could think about. And you just count. There are 26 red cards, 13 of them are hearts. So this probability is 13/26, which is the same as 1/2 or 0.5. What is the ordinary probability that a card is a heart? Unconditional probability. Okay, in this case, it's like you have a friend who looks at the card and tells you, hey, this card is red. And that affects your assessment of the likelihood that it's hearts. Because if you don't know anything about the card, other than it's from this 52 card deck, 13 out of 52 are hearts. This probability is 1/4. These are not equal. That means H and R are not independent. You could say dependent, but it's more common to say not independent. And it works the other way around as well. The conditional probability of being red when you know it's a heart, if your friend says, hey, it's a heart, and you know it's a standard deck, it's definitely red. This probability is 1. Whereas the ordinary unconditional probability of being red is 26 out of 52, 1/2. These are also not equal. R and H are not independent. Not independent. Are there events that are independent? Yeah. How about being a heart and being a queen? The conditional probability of being a queen when you know it's a heart is what? Out of these 13 hearts, only one of them is a queen right there. This is 1/13. On the other hand, the ordinary unconditional probability of being a queen, out of the whole deck, there are 4 queens. 1, 2, 3, 4 out of 52 cards total. This is 4 out of 52, which reduces to 1/13. These are equal. And it works if you switch them around. The conditional probability of being a heart when you know it's a queen, you're looking at these 4 queens, you've reduced the sample space to just these 4 queens, but only one of them is a heart. This is 1/4. And the unconditional probability of being a heart is 13 out of 52. That's also 1/4. These are equal. So Q and H, being a queen and being a heart, are independent. Okay, so this is just to illustrate this idea of independence or not independence. But again, in the problem itself, we're assuming independence. So we're assuming these equations are true. But how is that helpful? It comes back to the multiplication rule. We've talked about the general multiplication rule before. In this context, it would say the probability of C and D occurring is the probability of C times the conditional probability of D given C. And again, the roles of C and D are interchangeable. This is the same as the probability of D times the conditional probability of C given D. That's the general multiplication rule, that these two things are true. But wait a minute, since we're assuming independence, we could replace these two conditional probabilities with the appropriate probability up here. This probability right here could replace this one here, and this one right here could replace this one right there, and in either case, you get probability of C times the probability of D. These are unconditional probabilities. So the equality between these two things is sometimes called the special multiplication rule, or more descriptively, it's the multiplication rule for independent events. For independent events. Okay? And now you start to get an inkling that this might be useful, because you can now use the fact from part 1 to replace P of C with 2 times P of D and make this equal to 2 times P of D quantity squared for this problem. And piece of information 3 is that this equals 0.15. 3 says this equals 0.15, right? Because 0.15 is the probability that they purchase both collision and disability coverage, C intersect D. Use this, and you get 2 times P of D quantity squared must equal 0.15. Therefore, P of D is the square root of 0.15 divided by 2 is 0.075. Use my calculator now. 0.075 square root is about 0.27386. 0.27386. In the diagram, I rounded to 0.2739. P of C is twice that. P of C is going to be approximately 2 times 0.27386, which ends up being 0.54772. I rounded to 0.5477 right there in the diagram. That's the information we know. Now we need to focus on solving the problem here. Calculate the probability that the owner purchases neither collision nor disability, not C and not D. So we want to find the probability of C prime intersect D prime. Okay? Now, I'll prove this in a bit, but for the moment, let's just assume it's true. It should make intuitive sense that if C and D are unrelated, if they are independent, that probably C prime and D prime are unrelated, but they are independent as well. That should make intuitive sense, right? And therefore, this special multiplication rule would work for C prime and D prime as well. I don't need to use, for example, De Morgan's law here to try to rewrite this in some other way. This should be the probability of C prime times the probability of D prime, which is 1 minus the probability of C times 1 minus the probability of D. We know the probability of C and D individually approximately. So this is approximately 1 minus P of C would be 1 minus this thing. Let me do that in my head. That would be 0.45228. Hopefully I'm not making a mistake when I'm doing that in my head. Times 1 minus this thing is going to be 0.72614. I use the calculator to get the final answer. 0.45228 times 0.72614, about 0.328, which rounds to about 0.33, which is answer B in the sample exam. Okay, and I have labeled this area with 0.328. And so I do want to justify this step here, and I do want to go to Mathematica still, so this is still going to take a little bit of time here. But before I do those things, let me just talk about thinking about conditional probability as a relative area here. So I've labeled this fact here as well. Notice that this is 0.2739. The conditional probability of D given C is 0.2739, which equals the ordinary unconditional probability of D, because I'm assuming C and D are independent. What does that mean? I've talked about how you can think of conditional probabilities as relative areas. Because you're shrinking the sample space. Think about shrinking the sample space just to the red rectangle, because you're assuming C has occurred. What is the relative size of D in C, this intersection here, this rectangle, compared to the area of C itself? Well, it's about 27% of that area, a little bit more than a quarter. Just like the entire blue rectangle here is about 27% of the whole area of the black square. Okay? So as a relative area, not an absolute area, as this area divided by this whole area of the red rectangle, it equals the area of the blue rectangle. Okay? Let's justify this step here. Justification. To justify this, I do need to use De Morgan law. P of C prime intersect D prime is 1 minus the complement of that, the probability of the complement of that, which by a De Morgan law would be C union D. Then I can use the general addition rule to rewrite the probability of C union D as the probability of C plus the probability of D minus the probability of C intersect D. But because I'm assuming independence, this equals P of C times P of D, since I'm assuming independence of C and D. I'm trying to show C prime and D prime are independent. So this can now be written as 1 minus P of C minus P of D minus the product of P of C and P of D. And it may not be obvious at first, but this can be factored as 1 minus P of C times 1 minus P of D, and you can check that. Just FOIL these two binomials out, and that's P of C prime times P of D prime. Okay, so there's your justification. If you assume C and D are independent, that C prime and D prime are independent. I needed De Morgan's law plus the complement rule. I needed the general addition rule. I needed to use the assumption of independence, and then I need to do some algebra. Okay, and if this is true, they are independent. You can also say this kind of thing is going to be true when this probability equals this product. It will follow. I haven't proven that. It will follow that these two equations are true. It can follow from the general multiplication rule or the definition of conditional probability. Okay, I'll let you check that. Let's go to Mathematica now. And I've got some pretty neat things to show you here as well. Okay, so we're on video number 9, sample question number 11, and for video number 8 I didn't do any Mathematica. What do we have here? Well, first of all, I did put these things in here as functions of lambda. Remember that I still haven't done the extra part. I'm doing the extra part in Mathematica here. We now have the fact that I'm assuming, this is assuming, what? That lambda is the probability of C intersect D. Let me get my palette over here so I can make an equation more easily. P of C intersect D is lambda equals. Okay, that's the extra thing. That's what I'm using the Mathematica for here. And that ends up being by the assumption that C and D are independent. The product of P of C and P of D. And again, I'm assuming that P of C equals 2 times P of D. So this equals that. Okay, and that implies that if you solve for P of D in terms of lambda, P of D equals the square root of lambda over 2. Okay? So that's what P of D equals in terms of lambda. You can then solve for P of C as being twice this. That's what I'm programming Mathematica to do here, thinking of these things as functions of lambda. Then you can find the probability of C prime and D prime in terms of lambda, and you can see what it equals. And there's the answer. This is the answer to the extra question as far as what the probability of C prime intersect D prime is. Let me do a little copying and pasting to save time. C prime intersect D prime. What Mathematica is just showing us here with this calculation is that this is the answer. Okay? I'll say this means that the answer, if I can cut this out here, is this thing. That's the answer to the extra question. And if you plug in lambda equals 0.15 into that, you get the answer that we got, about 0.33 by hand, which was choice B. But now I want to also make some graphs. So this is going to make a graph of this thing as a function of lambda. Interesting function of lambda. It involves the square root of lambda. It involves a lambda itself. Here's what the graph looks like. And the black dot represents the answer to the question. When lambda is 0.15, the probability was about 0.33, which is what you see here. It's a decreasing function of lambda. As lambda increases, as this probability up here gets bigger, the answer gets smaller. And it's concave up, but it doesn't go higher than 1. When lambda is 0, the answer is 1. It does go negative, however, as a function of lambda. So we don't want negative probabilities. There is some value of lambda, looks like it's about 0.5, at which we don't want to go past. Okay, and in fact, if you solve that equation for where this thing equals 0, it does occur at lambda equals 0.5 and also 2, but 2 is not a valid probability. So the answer is lambda's got to be between 0 and 0.5. By the way, I'd encourage you to check that by hand. Set this equal to 0 and solve for lambda with this quadratic formula. It's a quadratic in the square root of lambda. And so you would get square root of lambda equals something, and you'd have to square both sides to get these answers. 1/2 is what we're after here, and again, the interval would be 0 to 1/2. And now I also want to make, here's the code for the picture, the static picture, but I also want to make an animation with manipulating Mathematica. And also show you some other formulas if you're interested. Here is the code that's going to make a animation of this as lambda changes. Lambda is set at 0.15 right now, but I can slide to the right, making lambda bigger, or slide to the left, making lambda smaller. If lambda gets bigger, remember the answer gets smaller. That orange area over here, this orange symbol representing the answer gets smaller because this area is getting smaller as lambda gets bigger. And as lambda gets smaller, goes to 0, then the answer over here gets larger. And no matter what lambda is, I've programmed this so that the relative area of the rectangle between the blue and red lines here compared to the red rectangle overall is the same as the area of the blue rectangle. Okay? I programmed it so that is always the case, no matter what lambda is. Okay? Hope you enjoyed that video.